Good afternoon, and first of all, I would like to thank Recon organizers for planning my talk afternoon, because in the morning it's quite difficult. Well, anyway, let's start. My talk will be about the decompiler internals. This is the presentation outline. I will talk about the decompiler architecture and see the microcode, the internal of the decompiler, see how we organize opcodes and operands, and talk about the problems that we encountered when building the decompiler, and some details about the data flow analysis and aliasability problems and other stuff. The online copy of this presentation is available at that URL. You can follow on the screen or from your laptop online. I think that you've heard about our decompiler. It exists already for more than 10 years now. We published the first one in 2007, and it was supporting only x86 at that moment, but over time we added many other target platforms to it. It is interactive, it's fast, robust, and programmable, so I think that we are doing good here. It requires IDA Pro to run, because it uses a lot of services from IDA, like the type management, function boundaries, and many other information comes from IDA. And the same way as IDA, it is very interactive. I mean that you can modify the code, modify the output, rename variables, and stuff like that. I hope that you know about it. So far, we haven't published the internal information about the decompiler, and this is something that we will do today. There were many reasons for that. The biggest one being that the internals keep changing, and once you publish something, it's too late. It's very difficult to modify the public API. If you are familiar with IDA, you will know that our API used to be so awful in the past, and we were criticized for that, saying, how come you have so bad names? But we had no choice, because there were other older plugins and we did not want to break the compatibility. And finally, with version 7 of IDA, we decided to switch to the 64-bit architecture. And at that moment, we could finally abandon the old API and build something new. Well, we did not abandon, because it's not a good idea to throw away decades of work, but we improved it a lot. This slide shows the general architecture of our decompiler. There are a few steps. I think that I discussed, I presented something similar in the past. So we have the following steps. We generate the microcode. We transform it by optimizing, resolving memory references. We analyze function calls, and so on and so on. At the end of this step, we end up with nice microcode that is ready to be converted into a C-like representation. But before doing that, we first allocate local variables. We create them. And then we create C tree. It's a syntax tree, an object that looks like a syntax tree used by compilers. We beautify it. This is a very insertional step that is required to have something very nice, readable. And finally, we print it on the screen. In our talk, we will discuss only the first two steps, because these are the most interesting part for us. Generating the microcode and transforming it. First of all, why do we need this microcode step? I think that everyone understands that we need it because, well, in my opinion, writing a decompiler without some intermediate language is a waste of time because, okay, we will end up with a nice decompiler for one platform. It won't be portable. So therefore, we need some kind of intermediate language. Language will help us to get rid of processor-specific things, like for x86, for example, there are segment registers that behave quite, I wouldn't say unusual because we got used to it, but it is different from how other processors behave. The floating point stack, which looks also somehow odd and not something common. In fact, every processor, I would say, has its own idiosyncrasy. I don't hear myself. That's good. It works now. ARM has the thumb mode addresses, PowerPC. By the way, that's a very interesting thing. We got used to have only one carry flag register. It's somewhere here, the contact. But on PowerPC, there are 4 copies of the carry register and of other registers as well. And it is possible to manipulate with them, to access them, to perform Boolean operations on top of them. And this is something that better the rest of the decompiler does not know. Of course, the part of the decompiler that generates the microcode needs to know about these particularities, but the rest should not care about it. So we keep the code simpler. MIPS has delay slots, Spark has stack windows, and so on and so on. So our first step is therefore to convert processor instructions into some kind of intermediate language. Now the question is it something difficult to implement? And should we implement a new intermediate language? What do you think? Is it that difficult? In fact, maybe it's not that difficult. But on the other hand, why should we spend time if there are so many existing intermediate language? Why did we implement the microcode? Intermediate languages used by LLVM, the famous Rail language, binary media, maybe it uses its own intermediate languages. There are many of them, and so on and so on. We could use something, but we did not. The main reason being that I started to work on the microcode and the decompilation problems way before all these languages existed. And our language also evolved over time. This slide shows how initially, let's say around 99, the microcode looked like this. You see that we have simple instructions like move, LDC stays for load constant, and suffix D means that the instruction works with double words. But currently, the microcode does not look like this. It evolved. I think that I started to work on microcode in '98 or even earlier, but I cannot find any records of it. The name is nothing fancy. It's just, well, just saying microcode because we take one processor instruction and we generate a dozen or sometimes less micro instructions. That's why the name was. Some design decisions turned out to be bad. In my opinion, it's very difficult to get things right at the first attempt. My estimate is that you need to try at least 3 times, maybe starting from scratch, to design something good. Because the first will be to throw away, the second time it will work with some inconsistencies, and the third time it has more chances to survive. For example, we have a problem with the notion of virtual stack registers. I will try to explain it later. We will fix these shortcomings, but it just takes time. Even today, we modify our microcode when necessary. For example, I reshuffle the instruction opcodes for this talk to make them more logical to make logical groups, and so on and so on. What are the design highlights behind the microcode? We want to keep things simple, especially at the beginning. No processor-specific stuff at all. The microcode is the same for all coprocessors. One micro instruction does simply one thing. There are no side effects at all. A very small number of instructions. The less number of instructions we have, the easier for us to handle things. Now we have 72. Back before we had even less. The instruction operands should be as simple as possible. Initially, in fact, we have only two types, registers and numbers, nothing else. And based on these two operand types, we can build everything else. We will consider only compiler-generated code for decompilation or analysis. Why so? Because for handcrafted code, the battle is almost lost because any instruction may mean anything else. So, for example, if you see in the listing something like increment EDX, it could mean, well, increment EDX may be not that bad because it's difficult to change its meaning. Do you think that it's because of that? Input here. Thank you. 1, 2, 3. Seems to be good. Thank you. There are things that we should decide not to care about because anyway we cannot handle them well. For example, instruction timing. When we decompile, of course, we will do some optimizations and some instructions may completely disappear or be replaced by something else. Therefore, we don't care about them. The instruction order, the same thing. We will reshuffle instructions to make nice expressions, and therefore we should not care about it. But there's a problem. If we reshuffle two instructions, for example, and the second of the instructions that generate an exception, after reshuffling, the second instruction may be executed before, and therefore the exception will happen earlier. This is a very tough problem, and therefore we just say, currently we don't support exceptions in our decompiler. And the order of memory accesses, it's somehow related to the exception handling. We don't preserve it neither. It can be reshuffled because of the same problems. Finally, we reached at the first slide that, no, not yet. The next slide will show you the microcode, how it looks like. Initially, it looks like a RISC code. It's very verbose, but it doesn't contain anything, anything complex. Let me show you. We have 4 instructions here, 2 moves, subtract and jump 0. And look at, they have the hexadecimal addresses, and they are converted into something like this. You see, it's much more verbose. We have lots of code here. We have, you can look at their instruction addresses to see how instructions got converted. For example, the first 5 lines represent one instruction. So you see that we manually, what was the instruction itself? It was a move from the memory pointed by EBX +4 into a register. And what we do, we first load the index register EBX and the segment register DS into some internal registers, and then we add them together, And finally, we load from the memory into temporary register. Then we move this, the value from the temporary register to EAX. You see, that's very verbose, and it can be simplified a lot. In fact, the first thing we do, we go over this initial very verbose microcode, and we make it shorter. You see what happened the next? The first instruction got converted into 1 micro instruction now. There are only 8 micro instructions in total, but it's still too noisy. Please note that we have now some sub-instructions appeared in the code. You see that EBX plus 4, for example, is present. It's visible as an operand of another instruction. This is, by the way, a very nice trick because it leads to nice expressions in the output, in the decompiler output. So we continue to optimize this microcode, and there are many, many steps, in fact. I don't show you all of them to you. I will just show you some intermediate transformation stage. You see now we ended up with 3 instructions: load from the memory, subtract something, and compare. And finally, we end up with just 1 instruction that does everything at once. It loads the value from the memory, compares it against the constant, 61, and if it's equal, then we jump somewhere. This code looks very nice and can be literally translated into C3 in a very straightforward way, and we end up with an if statement. As you maybe noticed, reading microcode is not that easy, but it was not designed for that. It was designed to make it so it can be analyzed easily, especially data flow operations. Data flow analysis should be handled nicely. We do spell out all operand sizes explicitly, and initially it was like RISC, but as we transform the microcode, it becomes not RISC at all. It becomes more like C expressions appear from, emerge in it. We implemented this translation step from the processor instructions to microcode in plain C++. We don't use any processor description languages, whatever. Well, I think that this is the price we have to pay to be fast. One of the things. And there are too many processor-specific details to be able to describe them in one nice language. So we do everything manually, and I don't see how we could do it otherwise right now. Maybe it's possible, but we'll see for the future. Now I will tell you a bit about all these microcode instructions. I will try to keep it fast because most of them are very logical and intuitive. For example, we have 2 instructions to load constants and move values from one place to another. The only restriction here is that we have the operands should be, sizes should be matched. They should all be of the same size. We call them left and destination here. There's also the middle operand, but it's not used in this case. Since real-world programs work with partial registers, we absolutely need to be able to work with different operand sizes. Therefore, we have instructions to extend value, signed, unsigned, and take a lower or higher part of a value. Naturally, we need instructions to work with the memory. Initially, we use them in the microcode because we generate a RISC-like code. So we have 2 instructions, store and load from the memory. when we refer to a memory, we refer using a segment and offset pair. The segment part is usually discarded for flat memory. That's what happens now, but this can be used in the future if you have different types of memory and you want to distinguish somehow. So we have the provision for that, but currently it's not really used. A set of comparison instructions. The comparison instructions work all the same. They compare the left operand against the right operand and store the result in the destination register. This is what we do to emulate processor condition codes like carry flag and others. The arithmetic and bitwise operations, nothing special, just the standard set of operations without anything fancy. We have the only thing maybe I have to tell is that signed and unsigned divisions and modulo operations, but it's not that interesting. The shifts, we have 3 shifts. This is enough. We also had rotations in the past. And it turned out that the rotations are not very useful in the microcode because we cannot do anything about them. They cannot be optimized into something better, converted into something nicer looking. So we keep them as is, and in the output, they will be represented as a call to an intrinsic function, and that's it. In some cases, well, not in some cases, in all cases, when we work with addition or subtraction instructions, we need to be able to calculate the carry and overflow bits, and for them we had to introduce very special instructions like the ones shown on this slide. Normally, they disappear during the optimization. And they get replaced by something else that is natural and very readable. The condition, the flow control. We have jumps we have 2 different kinds of jumps: indirect jumps and direct jumps that are called go-tos. The call instructions, both direct and indirect, and the return instruction. The slide also shows that a sample of a call instruction. You see that we have the function name, then for each argument, we also have the type information, the size information, and so on. Initially, this information is not available. Initially, we start with a simple call and the function name, or even a call indirectly by using a register, and then gradually we try to find out the function name and the prototype and so on. There is also a set of conditional jumps. Only JTBL maybe is interesting in this list. It is used for switch idioms when we use a table to jump to different locations. And finally, we have floating point operations. Again, there's nothing we can do about them because floating point operations are better not optimized, not modified at all. Every floating point operation is important by itself and cannot be replaced by something else without losing the precision or losing a possible exception. So we don't really optimize them. We just keep them as is. But we represent them nicely. And that's it. I think that we have the last group that it's some miscellaneous instruction operations. In fact, in this group, maybe the most interesting instruction is called external. The external instruction stays for anything else that our decompiler does not understand. Take, for example, AAM or some obscure privileged mode instruction. The decompiler will not die on that. It will still generate microcode consisting of the external instruction. For the external instructions, we cannot do much because we don't know anything about the semantics. Therefore, we just keep track of their data references. So what do they accept as the input and what do they modify? We need to have this information for the data flow analysis. Otherwise, we don't do anything about them. This is a quick list. We quickly reviewed all 72 instructions. Maybe we should extend the microcode or not, but we don't know. Anyway, this is something that to be discussed later. Now about the operands. We start with integers and registers, and it is very simple. And if you look at the many presentations, many of them just say, okay, we have these registers, numbers, and we try to solve some, prove something about the code using some theorem solver. Yes, life is very simple and easy for this case, but in real life we do have memory accesses, aliasable memory, and things become really, really complex because of them. Anyway, since we want to have to be able to express any real-world program, then we have to add more operand types. Therefore, we should be able to we need to be able to handle stack variables, globals. You see that there are many operand types we had to add over time. Let's go over them very quickly again. Our engine, that's a virtual machine that kind of handles this microcode. It has an unlimited number of microregisters, and the processor registers are mapped to microregisters. For example, AAX is mapped to 4 registers. So every microregister consists of 1 byte. So they have the fixed size. And therefore, AL is mapped naturally to the register number 8, and EH is mapped to register number 9. It is okay to allocate as many microregisters as we need to be able to represent processor instructions nicely, and we usually allocate them as needed when we generate. These are the examples of operands, register operands. EAX, RSI. You see, we always specify the operand size using a dot number. I was lazy in the past and decided to use registers to represent the stack frame of the function. It was saving me additional work of writing logic to handle stack variables in addition to the logic that I already had with registers. It looked like a bright idea because everything will be considered as registers and things become simple. In fact, it was not a good idea, and we still have this abstraction, and it really makes our life difficult because we will still need to handle indirect calls, indirect references to the stack frame, and microregisters do not work well. Anyway, that's laziness, that pays off, and not that great. Currently, the stack frame looks like this. From the point of view of the microcode, we consider, you see that at the bottom we have the local variables, and at the top we have the incoming stack arguments. And in the middle between them we have the return address, and sometimes for some processors we have also the shadow stack arguments area. And both the local variables at the bottom and the stack arguments at the top, they are divided into 2 parts, the red part and the yellow part. Why do we do so? Because of the aliasability problem. We need to know, since the decompiler tries to be sound and to generate correct code, we always need to prove that the transformations that we make are valid. And for that, we need to prove that, for example, a register did not change its value from the point A to the point B, but if we have some function call in the middle, we don't know what this function will do. And then we cannot prove anything. So in order to be able to prove something, we need to keep track of what is aliasable and what is not. Our current approach is very simple. We keep track of what is aliasable. Anyway, I will tell you about it slightly later. Right now, I will just tell you that everything yellow is considered to be unaliasable, so therefore we can reason about that part of the stack frame in a strict manner and prove things. We had to introduce more operand types over time because well, everyone starts with simple registers and says, and he's proud saying, oh, it works great. But there are many minor details, like for example, 64-bit values in the on 32-bit platforms. There we have the following problem, because one register cannot hold the entire value. Therefore, well, usually we use a standard pair like EDX and EX. But nowadays, compilers are very, very clever, and they can use any pair of registers to hold such a value. And sometimes they even hold a part of the value in the memory and another part on the register. To be able to represent this kind of stuff, we had to introduce a new operand type. It's called operand pair, and the halves are completely independent of each other. They need to be of the same size. That's the only restriction on them. But it was just the beginning of the nightmare with a microcode, because modern compilers can be very aggressive when they use registers and memory. And for example, some of them pass complex structures and unions by value to the called functions. They follow the ABI. The ABI says that if you have a big structure, it should be passed partially on the registers and partially on the stack. And some of the fields may be even on floating point registers. And therefore, so we have a really complex situation here, and we had no other choice but to add the so-called scattered operands, and they can represent all the above. I have just one small example here. Let's imagine that we have a function that returns a structure. A structure consists of two integers, and they are returned, in our case, in one register. So the whole structure is returned in one register. It's a very common situation. And the assembler code, as you see, we call the div instruction, and then we take low part of the register EAX and put it aside, and we take the high part of the same register and extract another field from the return value. That's how the processor works. And this code should be converted into something nice. And we do that exactly because we can handle scattered return values, scattered operands in general. You see that we assign the return value into V2, and then the V2 is a structure, and we can access separate fields of this structure in two different assignments. Even more complex situations exist for all 64-bit processors, because all of them use this kind of structures or scattered operands. It's defined by the ABI. So any decent decompiler should have support for them in one way or another. Unfortunately, it's quite difficult to handle. It's a research, and we don't have a complete support for them. In some cases, the compiler may tell you, sorry, I could not handle this or that particular case, but we are working on it. Once we generated the microcode, we work on optimizing it to make it simpler, shorter. I already showed you the first pre-optimization step. That was using a very simple constant propagation algorithm. It works only with constants and registers, and it's because of that it's very, very fast. But it gets rid of most temporary registers and reduces the size, the microcode size by 2. But normally, after that, we use more sophisticated algorithms to optimize and transform the microcode. We start first at the basic block level, and we first optimize each basic block individually by propagating register values, even partial registers. For example, if you propagate a wide EAX register into a small instruction that handles only bytes, this can be handled. So we can move one instruction inside another, and it can also optimize the stack, global memory, and other things. Once we handled all basic blocks individually, we try to optimize things globally. For that, we build the call graph. And this way, we know which basic block, what are the flow controls, control flow transfers. And then we can perform data flow analysis and further optimize the code by deleting the dead code, propagating operands across block boundaries, and other kinds of optimizations. By the way, we do the following trick. If you have a flow chart like this, when the false branch is taken, we know for sure that EIX is equal to 0, provided if there are no incoming arrows to that block. Therefore, we generate a new synthetic move instruction saying that EIX is kind of assigned 0. This instruction was not existing initially in the input code, but it helps us to optimize the code better because we can replace EIX in this block by zeros. The optimization engine is, in fact, I consider it as very simple because it consists of simple rules. We have kind of obvious rules. I tried to give you some of them here. For example, x minus y plus y, it's the same thing as x because we did not do anything else. And we have literally hundreds of very small optimization rules. They are sound, they can be applied in all cases, and if not, they will be preconditioned, and the precondition is checked before we apply the rule. And they don't depend on the compiler, because regardless of the compiler, the rule is sound and correct. It should work. And sometimes people ask us, what about the compilers? What compilers do you support? And we usually say, well, just try. Normally it should work because the rules are the same for all compilers. We should produce some nice code for almost any input, and regardless of the input language even. So the code can be written in Fortran. We will still convert it to C because we don't know to produce any other code, any other output, but it should be correct. Of course, not all our rules are simple. Some of them are complex. Say, for example, here we have a rule called CMB 18. It combines two instructions that handle a low and high part of a subtraction into one nice subtraction instruction. And it has some conditions saying that the y high, which means the high part of the y operand, is 0, then this can be optimized away. Otherwise, there are some special cases, and so on, so on, so on. We have literally hundreds of rules like that. Everything hard-coded in C++. And they work like small little ants that every ant does its job and finally, at the end, we have nice output. That's how it works. Of course, the rules that we use should be not that stupid. When we talk about pattern matching, yes, we do use some pattern matching in the decompiler. We don't naively apply a pattern to the code for matching. For example, if you have a pattern saying that we have, here we have rule number 43, it says multiplication, and after the multiplication, there should be the low instruction. We don't compare mul and then low. Instead of that, we build the lists, so-called data access lists, and then we search for the instruction that accesses. For example, in our case, we try to find the instructions that accesses the X operand. And when we find it, we check if it's a low instruction, does it look like the one that we expect to see? If it's the case, then we apply the rule. And this approach allows us to recognize patterns that are interleaved with other instructions, or even sometimes we tolerate some shuffling of instructions as well, then when the order is changed. So we work with data dependencies. So data dependency rules are dependent on the data. Another kind of rule, another example of a rule is a rule that works across multiple basic blocks. On this slide, I have a 64-bit comparison. Unfortunately for us, the 64-bit comparison is performed using 3 32-bit comparisons on 32-bit processors. There is no other way of doing it. We first compare the high parts, if they are equal or not. If one is less than the other, we already go to the success block. Otherwise, we compare the high blocks for if they are greater. If not, then they must be equal. Therefore, we have to compare the low parts to decide what happens. The decompiler can recognize this pattern and convert it into simple one line when we say jump less, X, Y, and success. Another example, division by power of 2. It is represented by 3 instructions. Check if the X is negative or not. If it's not negative, then we simply shift to the right arithmetically. Otherwise, we have to add a correction which makes the shift correct even in the case of negative numbers. And the transformation rule gives us back a very nice sign division instruction. Why do I tell you about all these rules and how they look like? It is because we are going to open microcode, so you can use it in your projects, and you will be able to hook to the optimization engine and to add your own little transformation rules, which this way you can handle many different things, like maybe you can handle some obfuscated code or some special idioms generated by by the compiler or anything else. Currently, it is not possible to affect the rules that already exist in the compiler, so they are always active, you cannot disable them, but we will see if it becomes really a problem or not. I hope that it's not really a problem. So let me give an example. For example, the ARM decompiler has the following rule. If you have an indirect jump that uses the initial value of the LR register, then it can be safely converted into the return instruction. And such a rule can convert BXLR into a simple return instruction, which simplifies the code, of course. But to apply this rule, we have to prove that the LR instruction at the indirect jump is exactly the same as we had at the entry point. And this is the task of the rule to prove that. And in fact, the proof is quite simple. We just remember the value of LR. Usually it's saved somewhere on the stack, and we just prove that the stack value, the value that comes from the stack slot has not changed by the process by the function. So we use data analysis to prove that the LR is the same as before, as the initial value. If you talk about data flow analysis, we use it extensively. In fact, internally, the decompiler is based on the data flow analysis pretty much, I would say, everywhere. Maybe you already noticed that on my slides, all the micro instructions had in the comments U equal and D equal notations. I highlighted them in red on this slide. So we see that, for example, the move instruction accesses argument +4, so it means that the second argument, and defines the EBX register. These lists, we call them use and def lists, they are calculated on the fly, and it's very easy to ask the decompiler what this particular instruction modifies or uses. And after that, the use def lists are used to find another instruction, the way the value comes from, and so on, so on. We maintain similar lists for the basic blocks. For each basic block, we have the used list, defined list, and defined but not used. D and new stays for defined by not used locations. We keep both must and may access lists. So for an instruction, we can talk about the must access. So the instruction must access this memory cell, and on the other hand, may access. For example, for an indirect load like LDX, we can say that it may access any memory, because we don't know, usually we don't know what is the value of the indirect register is, but we cannot say which memory cell it must access, because again, we don't know what exactly. It may access everything, but we don't know what exactly. Therefore, we keep both of these lists separately, must access lists and may access lists. And naturally, all these use def lists are very, very useful for the decompiler, because they can be used to answer questions like if a particular value defined anywhere, or if it's used anywhere. If it's used only one location, then what about migrating the instruction completely to the use place, so we can get rid of it completely, maybe? If not, then what is the use of keeping it? Maybe we can delete it. And there are many questions like that, and we try to answer these questions, and this way we keep all our analysis sound. It's not something that we decide to apply pattern just because it looks nice to us. There is some kind of, the decompiler needs to prove something before applying it. The use def lists also used to propagate values globally. Let me show you an example. Imagine that we have the code like we move number 5 into a register, then do some stuff that does not modify that register, and then we use it in a call. If we can prove that the block number 2 does not modify ESI, then we could simplify it. We could simplify it into simply call function 5, and the argument is 5. For that, we use the use-defined blocks generated by the decompiler and prove. And you see that the first block has a def list that ESI, which is used only in the block number 3. And on the other hand, the block number 3 says that we use the ESI that comes now from the block number 1. So by looking at these two pieces of information, we can decide it is very safe, no problems at all. We can get rid of the instruction in the block number 1 and propagate the value 5 directly into the block number 3. So we use the standard data analysis things, well, algorithms that you can, that maybe you know about because so they are part of any computer science course. But the devil is in the details as usual. For example, first of all, we need to be able to handle partial registers. They are paying, to tell the truth. We need to handle big endian, little endian as well. And when you talk about partial accesses with big endian and little endian, then things become really, really complex. Sometimes we end up with well, funny, I wouldn't say that funny situations when part of an operand is little endian because it's already in the register, and another part is still on the memory, and therefore it's big endian. So when we need to know the endianness, we need to specify which part of the operand do you mean. Our data flow analysis can handle stack frame and registers. By the way, we don't use SSA. It's not that we have something against it, but it's just the iterative approach works reasonably well. And usually when you talk about a cell, we will talk about these variables. And the problem is that at that moment, when we have this data flow analysis, we don't have any variables yet. We don't know their boundaries. So, of course, we could talk about each byte individually, but then you end up with literally thousands of variables that map to each micro-register, and then everything becomes horribly slow. That's one of the reasons we keep to our approach. By the way, we have very fine, very nice granularity because we don't access every stack location individually as a byte, but we split the stack into separate regions that can be considered as, that can be used as separate entities for data flow analysis. And when we talk about stack locations, you remember that we have to tell about aliasability. Then we have to make some assumptions. And the assumptions are an interesting thing. Let me show you a couple of slides about them. The decompiler, so far, I was telling you that it is sound, it produces precise code. Yes, but there are some stuff that is lost in the translation and not present in the binary file. For example, the function prototypes, the function arguments, this information is not there. Look at this code. We have push, two moves, another push, and then finally we call in function. Can you tell me how many operands, how many arguments this function call has? The problem is that we cannot. In general case, we cannot tell safely we know the function prototype because it can be anything. For example, the first push could be part of the function prologue or a temporary save, register save, or an argument. And the same algorithm, the same logic can applies to all 4 instructions. We don't know. Therefore, the decompiler has to guess. It guesses 90% of time nicely, maybe 95. I never calculated the success rate. But anyway, there is a danger of guessing it wrongly and producing wrong code. But fortunately for us, the user or you using the SDK can tell the decompiler, I know the prototype of this call, please use it for the decompilation. Another place when the decompiler has to make some guesses. The following example, we move number 1 into the stack variable, then we store 0 to the memory location pointed by EAX, and then we call a function using our stack variable. Can we claim that at the call we have stack variable equal to 1 or not? No, we cannot claim that. We don't know the information because the second instruction, the indirect store, could overwrite the value 1 in the stack variable. But in some cases, we can claim that we know that it's still equals to 1. For example, if you haven't taken any address of any stack variable. So we can consider that the stack variable, the stack frame, it cannot be referenced indirectly. If you talk about the handcrafted assembler code, this assumption does not hold, of course, because in assembler you can abuse any assumption. But since we decided, okay, the assembler handler, the handcrafted code is out of reach for us, we will focus on the compiler-generated code. And therefore, we can take such an assumption. You remember the slide that I showed you, and it was these yellow and red areas. And the red area, how do you calculate the size of the red and yellow areas? That's another interesting question. And there, we have to employ a special logic to calculate something called, stack references. We calculate the minimal stack reference. Unfortunately, this problem is, again, unsolvable in general. And therefore, we try to be on the safe side, and we optimize only the things that we prove that we calculated the correct stack reference. We have something called minimum stack reference. I told you about it. And we currently keep one value of mean stack reference per block, but maybe we could improve it. Let me show you an example, in fact. We have the following case when we have two calls to the function, to the same function, but please note the difference. In the first case, we take the offset 10 from the stack pointer, and in the second case, we take an offset of another variable as the offset 12 from the stack pointer. In the first case, the decompiler assumes that the offset 14 could be spoiled by the called function because we passed offset 10 to it. On the second case, we don't know for sure, but we assume that that function will not access the memory lower than 20, therefore access the memory cell at the offset 14 can be considered kind of safe. Well, let's say it's not completely true, but it holds in real life, therefore we can live with that. If we remove this logic, the output of the decompiler will become much worse because we will not be in position to optimize some code, and the code will look ugly, and the readability will suffer because of that. Now about ensuring that the microcode that we work with stays consistent and sane. For that, we have some verification routines that are used to, in fact, we call them every time after each transformation. And third-party plugins, your plugin should do the same. And we will publish the verification routines as part of the SDK, so you can see what are the requirements to the microcode, so you don't spoil it by mistake and end up with very wrong results. Therefore, thanks to these verification routines and thanks to the fact that we run literally all the time different tests of the decompiler, we have pretty much very little number of complaints about the decompiler. But if you encounter any problem with the decompiler, you are free, of course, to tell about us. We try to solve the problems within 1 day or even sometimes faster. It works quite well. So, as I told you, we will publish the microcode. First, it will be available only as C++, because I think that we will continue to change it a bit. So your feedback is very interesting because it will help to improve the microcode and make it really useful for many maybe unforeseen, even new kind of analysis. Maybe you can even work maybe you can even write something to handle obfuscation code of that opaque predicates and things like that. Python will be available later, and we will start beta testing the next week. So if you are interested, just send us a message saying that you want to participate. And we will also provide the sample plugins that that show you how to work with the microcode, how to generate microcode, and other stuff like that. Oh, well, I think that's it. Thank you for your attention. I hope it was not very boring.
Questions? You have to come over here.
Yes, so first, thanks for the talk. It's very interesting. I was wondering, given your experience of working with this for 10 years and the other intermediate language out there, what would you have done differently if you could start over, besides the problems you've discussed, like the mapping of the ESP to the register and the scattered and the paired operands? Would you have completely designed a different microcode, given in hindsight? Maybe you can briefly discuss some things, or?
I'm sorry, I did not quite understand the question. It's about scattered operands?
No. So you've been working with your microcode now for 10 years.
Yes.
And so you have a lot of experience with what can go wrong and the things you've designed in a way how it backfires now. Yes. And given the other intermediate language out there, I assume you have researched them as well. What would you have done differently now if you could restart?
Okay, got it, thank you. What would I have done differently today? In fact, every time I saw that something was not quite correct and I started to regret it, I tried to fix it. So currently the microcode is already very different from what it was before. Therefore, yes, there were many mistakes, and most of them are already kind of solved now. Maybe that's a big exception is that mapping of the stack frame to micro registers was a bad idea, and I would have done it differently. That's one big thing that I would have done differently. Otherwise, since the microcode was not published all these 10 years, the bad decisions, we could revert them without paying the public price and shame. So yeah, we did many mistakes. That's true. I think that nobody can claim that he's without any. He can do everything at the first time correctly, but we corrected them. I think that that's the most important thing here. So to correct the mistakes when they become really a nuisance or a big problem.
Thank you for the presentation. I was wondering how you, on your left.
Oh,
here,
yes, good.
How do you keep track of the original address once you start optimizing and merging microbes? Because you can switch between the decompiler and the original assembly code. So how do you keep the link between the high-level view and the original assembly code?
Thank you. It's very simple, in fact. Every micro instruction has an address. And when we propagate, we keep the address together with the instruction. It's a natural part of the micro instructions. Well, that's part of the definition. And that's enough most of the time. In some cases, we do have some problems with this approach because, for example, we generate assertions. I showed you. Sometimes we generate new micro instructions on the fly. They were not existing before. And there we have to use some address. And then we come up with We cannot use any random address because it would be wrong as well. Therefore, we reuse the address of the next instruction. That's a bit of cheating, but okay, it works. Another transformation we do is that sometimes we have a call that gets duplicated in the output. It's so-called unmerging of calls, call unmerging. And for that, we also need to have, we end up with two different calls. We started with one call, and we have now two calls. And for them, we need to assign different addresses because we need to be able to distinguish these two calls now. And again, we cheat a bit, and we say, okay, this, for example, this call is address A, okay, and we assign to that call A+1. We are safe because A+1 normally it doesn't clash with anything else. But there's things like that. They again sound. They don't lead to any problems in practice. But we do these kind of things from time to time.
So you mentioned you have a few hundred simple rules, passes, optimization passes. But I imagine the output from one might match the pattern, input pattern of another one. So how do you ensure that the passes converge and actually create cleaner code and don't de-optimize something that an earlier pass did?
So how do we keep things in control so it doesn't get out like into something unreadable, very long? Well, we try to do the following things. First of all, we reduce the complexity. And if we see that after moving one player, propagating, the instruction becomes too complex, we have some complexity measure, then we don't do it. It's a transformation that does not help us at all. Second, how do we organize these optimization phases? I wouldn't call them the phases because they are so small and they are just, we do this, we have this transformation rule, try another rule immediately after that. And we try them until we reach the fixed point. It's, since we always try to optimize and improve the score, normally we should not get into an endless loop. Unless you write a third-party plugin that will spoil the microcode and unoptimize things, and something inside the microcode will, the engine will improve it, and then we'll have two rules that fight each other. It may happen sometimes, but normally, well, I don't think that any of our users complained about it. Did I answer the question, or I lost track a bit?
He says yes.
Hi. I would like to know if you can elaborate on what kind of instructions do you translate, meaning what kind of instructions get semantic and what kind of instructions don't. So for example, you said that you dropped these semantics for rotations. And does this mean that you translate only those instructions that can be some reasonably represented in C? And the second part of the question, if so, then doesn't sometimes become situations when you say that only if I knew what that instruction that I didn't translate does, it could somehow help me to do some other analysis if I had that semantics?
Yes, we translate to microcode only the instructions that can be mapped to it. Well, anything that cannot be mapped, like I don't know, like a square root, then we leave it as is. We leave it either as an external instruction, or either sometimes we do so-called intrinsic call. We replace such an instruction by a call to a function that's called the square root. In practice, it works well, because the end user sees it's square root. It matches his expectations. So no problems at all. But if you want, and it happens in practice, and if you want to handle some unsupported instructions that are represented as external instructions, you can write a transformation rule. Still, it's possible to write transformation rules. Why? Because every micro instruction has an address, as I answered previously. Since you have the address, you can look up the exact instruction in the IDA database and decide how to optimize it. That's one possibility. Another possibility is that you can write transformation rules on top of intrinsic calls. You have this intrinsic call plus that intrinsic call. They do something together. A combination of them can be simplified into something else. In practice, we do have this kind of rules for XMM-related instructions. We convert all of them to intrinsic functions. Thanks to Intel and Microsoft, we have most of them covered. They can be represented as intrinsics. And then after that, we have rules saying that if you have two different intrinsic calls, they can also be simplified further. And you may end up with something very simple like 5 plus 2 floating point, of course.
We only have time for one more question. If anybody has any more questions, you should probably find Ilfak after the talk.
Hey, thank you for the interesting talk, sir. I would like to ask a question also about the decompilation, the disassembly, not only the decompilation. There is some very unique architectures with strange concepts, like last year talk. There was talk about reversing HSM, cryptographic models, and with assembly syntax that including running different commands on parallel cortex. How does your decompilation and disassembly manages to work with it?
Okay, so it's about parallel execution and odd instructions. I don't know about decompilation yet because we haven't talked about such odd architectures for decompiler. We don't have a notion of parallelism in the decompiler yet. So this is something that we'll have to add if we decide to support such things. But let's talk about disassembling first. Either can handle parallel instructions and represent them nicely. In fact, we do have some processor models doing that. I think that one of the Texas Instruments TMS 320 chips, they have parallel instructions. Well, we just show them on two different lines, two lines, and that's it, and it's up to you to read. In fact, IDA has a very little understanding of the program. It's a disassembler. What it does is just takes opcodes, converts to text, and shows to you. Of course, it has some no understanding of the instruction semantics, but very limited. There is no data flow control. And after we publish this microcode engine, we will use micro data flow analysis engine from the decompiler in IDA as well. So IDA will not have the data flow analysis never. But it's pretty much, it works pretty much well in IDA. No problems at all with these odd instructions. Even we have some processors having algebraic form instructions when you have this floating point. Usually this happens with DSPs. IDA can handle them very well. And you have the source code. You can look at the source code in this decay.
Thank you very much, Ilfak.
Okay, thank you.